the name of Almighty God, I'm Master Sankocha, and today I want to talk about introduction about wave optics module. The wave optics module is used by engineers and scientists to understand, predict, and design electromagnetic wave propagation and resonance effects in optical applications. Simulations of this kind results in more powerful and efficient products and engineering methods. It allows its users to quickly and accurately predict electromagnetic field distribution, transmission, and reflection coefficients and power dissipation in a proposed design. Compared to traditional prototyping, it offers the benefits of lower cost and the ability to evaluate and predict entities that are not directly measurable in experiments. It also allows the exploration of operating conditions that would destroy a real prototype or be hazardous. This module covers electromagnetic fields and waves in two-dimensional and three-dimensional spaces. All modeling formulations are based on Maxwell's equations together with material laws for propagation in various media. The modeling capabilities are accessed via predefined physics interfaces, collectively referred to as wave optics interfaces, which allows you to set up and solve electromagnetic models. The wave optics interfaces cover the modeling of the electromagnetic fields and waves in the frequency domain, time domain, eigenfrequency, and modal analysis. Under the hood, the wave optics interfaces formulate and solve the differential form of Maxwell's equations together with the initial and boundary conditions. The equations are solved using the finite element method and the boundary element method, which numerically stable edge element discretization in combination with the state-of-the-art algorithms for preconditioning and solution of the resulting sparse equation systems. The results are presented using predefined plots of electric and magnetic fields, reflectance, transmittances, and diffraction efficiencies and S parameters, power flow, and dissipation. You can also display your results as plots of expressions for of the physical quantities that you define freely, or as tabulated derived values obtained from the simulation. The workflow is straightforward and can be described by the following steps: define the geometry, select material, select a suitable wave optics interface, define boundary and initial conditions, define the mesh, select a solver, and visualize the results. All these steps are accessed from the computer desktop. The geometry can be built from basic geometry shapes or parts like waveguide elements can be added from the wave optics parts library. Materials can have user-defined properties or they can be picked from any of the built-in material in libraries, including the optical material libraries. The libraries includes more than 1,000 inorganic and also organic materials, glasses, and so on. The mesh creation and solver selection steps are usually carried out automatically using default settings, which are turned and tuned for each specific wave optics interface. The wave optics module application library describes the physics interfaces and their different features through tutorial and benchmark examples for the different formulations. The library includes examples addressing grating and metamaterial, laser cavities, nonlinear optics, optical scattering, waveguides, and couplers, and benchmark models for verification and validation of the wave optics interfaces. And this introduction is intended to give you a jump start in your modeling work. It has examples of typical use of the wave optics module, a list of the physics interfaces with a short description, and a tutorial model that introduces the modeling workflow. Now I'm going to go through the use of the wave optic modules. The wave optics interfaces are used to model electromagnetic fields and waves in optical applications. Typical wavelengths for optical applications are in the nanometer to micrometer range, corresponding to frequencies of the order of hundreds of terahertz. A characteristic of optical applications is also that the structures are often much larger than the wavelength, Wave optics simulations are often used for determining propagation and coupling properties for different types of waveguide structures. Figure 1 shows the electric field distribution in a directional coupler. A wave is launched into the left waveguide. The wave couples over to the right waveguide after 2 mm propagation. The waveguides consist of ion bombarded and surrounded by the gas. The figure 1 shows electric field distribution in a directional coupler. Nice stats the propagation length is 2 mm, whereas the cross-sectional area is 12 micrometer by 18 micrometer from directional coupler in the wave optics module application library. You see that we have an electric field norm based on the volt per meter, and this is a legend, the right sections, and it's showing the frequency based on the first frequency is 260 about such as. Figure 2 shows an example of transient propagation and nonlinear crystal. The figure shows the total electric field, the sum of the incoming fundamental wave and generated second harmonic wave when the wave is located in the middle of the crystal. You see the electric field, and figure 2 shows the Z component of the electric field after 61 frequencies propagation in a nonlinear crystal from the second harmonic generation of a Gaussian beam in the wave optic module application library. Transient simulations are useful for modeling nonlinear optical processes involving short optical pulses. Another example of nonlinear optical propagation is the effect of self-focusing, as shown in figure 3. Here, the Gaussian beam and the intensity-dependent refractive index from the self-induced lens in the material that contracts the spreading effect of the diffraction. Figure 3 shows the electric field distribution for Gaussian beam propagation in a medium with an intensity-dependent refractive index from self-focusing in the wave optics module application library. In Figure 4 and Figure 5, a model from the wave optics module application library shows the scattering of an incoming plane wave by a small gold sphere. The model is set up using the scatter field formulation where the incoming plane wave is entered as a background field. The scatter wave is absorbed by a perfectly matched layer PML. Figure 4 shows the volume resistive losses in the blue gold sphere. Figure 4 illustrates the volume resistive losses in a small gold sphere when excited by an incoming plane wave from the optical scattering of a gold nanosphere in a wave optic module application library. A far-field domain is used the model to calculate the far-field pattern of the scattered waves as shown in Figure 5. In Figure 5, you see the radiation pattern far-field norm based on the volt per meter, radiation pattern far-field form norm based on the volt per meter. Figure 5 shows and illustrates the far-field radiation pattern in the E-plane blue section and the H-plane beam lines when wavelength is 700 nanometer. The wave optics module also offers a comprehensive set of features for two-dimensional modeling, including both source driven wave propagation and mode analysis. Figure 6 shows the mode analysis of a microstructure optical fiber. You see effective mode index is equal to 1.44 tangential and longitudinal electric and magnetic fields. The tangential you see there is a and in the both the electric field and magnetic field you see is almost the same, and also in the longitudinal in electric field and magnetic field also are the same, but the difference that the focus is in four node, but here in the magnetic field there is in the two nodes. Figure 6 shows the surface plot visualize the norm of the tangential and longitudinal electric and magnetic fields for one of the two degenerate He11 like modes for a wholly fiber from leaky modes in a microstructure optical fiber in the wave optics module application library in both two dimensions and three dimensions. The analysis of periodic structure is popular. Figure 7 is an example of a plane wave incident on a metallic wire grating with a dielectric substrate. Figure 7 illustrates electric field norm for T incidence at P divided by 5 radians from plasmonic wire grating in the wave optics module application library. Figure 8 shows the resulting plot of the reflectances, transmittances, and diffraction efficiencies. Figure 8 shows reflectance and transmittance and diffraction efficiencies as a function of angle of incidence from the plasmonic wire grating in the wave optics module application library. Figure 9 shows an example of polarization plot. The polarization plot shows the state of polarization for different diffraction orders for a periodic structure. And in this example, the periodic structure is a hexagonal grating. Figure 9 shows polarization state plot showing polarization ellipses for different diffraction order for a periodic structure from hexagonal grating in the wave optic module application library. Eigenfrequency studies are of interest of a photonic band gap structure and laser cavity calculation. Figure 10 shows the mode field for a vertical cavity surface emitting laser (VCSEL) after self-consistent solution for the resonance frequency and the threshold gain. Figure 10 shows the model field of a vertical cavity surface-emitting laser for a self-consistent solution of the resonance frequency and the threshold gain. From the threshold gain calculations for vertical cavity surface-emitting lasers in the wave optics module application library. The wave optics interfaces can easily be combined with physics interfaces from other physics areas such as heat transfer, structural mechanics, semiconductor physics, and lab frequency electromagnetism. Figure 11 shows the result of a multiphysics simulation combining the electromagnetic waves frequency domain interface from the wave optics module with the electrostatic and the weak form PD interfaces from the Capsule Multiphysics platform product. Using these three physics interfaces, the Austen-Frank equation is solved for the distribution of the director's optical axis in the impedance switching IPS and pneumatic liquid crystal cell under an applied static electric field. The wave optic interface solves for the electric field for the wave for this anisotropic and inhomogeneous liquid crystal material. Figure 11 shows the director optical axis distribution arrows, the electric potential slice plot, and the static electric field as the streamlines for an in-plane switching IPS pneumatic liquid crystal cell from an in-plane switching of a liquid crystal cell in the wave optics module application library. The wave optics module has a vast range of tools to evaluate and export the results. For example, evaluation of far field and scattering matrices. Parameters can be exported in the Touchstone file format. Now I'm going to go through the wave optics module physics interfaces. The wave optics interfaces are based upon Maxwell's equations together with materials law in the module. These laws of physics are translated by the wave optics interfaces to sets of partial differential equations with corresponding initial as boundary conditions. The wave optics interfaces define a number of features. Each feature represents a term or condition in the underlying Maxwell-based formulation and may be define the geometric entity of the model, such as the domain, boundary, edge, for three dimensions, components, or point. Figure 12 shows and uses the plasmonic wire grating application from the Wave Optics Module Application library to show the Model Builder window and the settings window for the selected wave equation electric 1 featured node. The wave equation electric 1 node adds a term representing the Helmholtz wave equation to the model equation for, in this case, all domains in the model. As this is an example of a periodic problem, the wave equation electric 1 node is a subnode to the periodic structure 1 node. The wave equation electric 1 feature node may link to the material feature node to obtain physical properties such as relative permittivity and refractive index. In this case, the refractive index of the user-defined dielectric, the properties defined by the dielectric material, can be functions of the model physical quantities such as temperature. Also, the first material, air, is in this case a user-defined material, whereas the third material, the gold wire labeled Iurakic, is taken from the optical material library. The simulation domain is delimited by boundary condition feature nodes. The default boundary condition feature for the physics interfaces in the wave optics module is the perfect electric conductor feature. For the example in the figure 12, the top perfect electric conductor 1 feature node is overridden by the periodic structure 1 node. However, the perfect electric conductor 1 subnode to the periodic structures 1 feature node is overridden by two periodic port feature nodes and a fluctuate periodic condition feature node. The periodic port features are used for exciting and absorbing waves, and the fluctuate periodic conditions relates fields on parallel opposing boundaries with fluctuate periodicity conditions. Figure 12 shows the model builder in the left side and the setting window for the wave equation electric in the right section. The equation section shows the model equation and the term added by the wave equation electric node to the model equations. The added terms are underlined with a dot line. The text also explains the link between the dielectric node and the waves for the refractive index. Figure 13 shows the wave optics interfaces as displayed in the model result. For this model, you can see we have a ray optics, wave optics, and wave optics. We have a subsection as different and various physics interfaces such as electromagnetic waves, beam envelope, electromagnetic waves, boundary elements, electromagnetic waves, frequency domain, electromagnetic waves, time explicit, electromagnetic waves, transient, electromagnetic waves, finite element method, and boundary element method. This module includes wave optics interfaces for frequency domain modeling and time domain modeling respectively. It also includes the laser heating interface available under heat transfer. Also see physics interface guide by space dimension and study time. Thank you so much for watching my tutorial video on today. And also you can download the related file, simulation file from github/script. Today is 28th of April 2026. Time is 1:12 a.m.